The next thing we need to talk about is the uniqueness of b to the x. So we're just going to briefly talk about this and remind ourselves before we go into solving some more complicated logarithmic equations. So this property says that if b is greater than 0 and b is not equal to 1, so that's been true for all of our bases, then b to the x equals b to the y is equivalent to x equals y. Essentially, that's saying if they have the same base, then their exponents have to be equal too, which makes sense, right? I couldn't have 2 to the 4th power equaling 2 to the 3rd power. That's not equal, right? They're going to give us different values. So that's all this is saying that if the two bases are equal, the exponents have to be equal as well. So if I have an example like this, it says solve 5 to the x equals 125. So right now, this doesn't look like something I could solve. But 125, if I factor it, is the same thing as 5 times 25, and 25 is 5 times 5. So it's 5 cubed. So I could rewrite 125 as 5 cubed. And now they have the same base, which means their exponents must be equal, which means x must be 3. Go ahead and try the example on the right-hand side. Alright, this one was a little bit harder. It's 3 to the x equals 1 over 81. So I do know 81 is the same thing as 9 times 9, and 9 is 3 times 3. So I end up with 81 equals 3 to the 4th power. 1 over 3 to the 4th power. But this base is in the denominator, and that base is not. So how do I get this out of the denominator? I would need to take the reciprocal. And what happens with the negative or with the exponent when I take the reciprocal? It's going to become negative, because it wasn't negative, now it is negative. So now we have the same base. 3 to the x equals 3 to the negative 4, and x will equal negative 4. We can always plug these back into the original and check them to make sure they're true. So that's just a little refresher about using this property. When we have the same base, the exponents must be equal. Now let's get into these log equations. First example says log base 3 of 81 equals x. To solve a log equation, I'm going to rewrite it exponentially. Log base 3, so the base is 3, logs equal the exponents, so that equals x. And that will equal what we took the log of, 81. And we just learned a few minutes ago that 81 is the same thing as 3 to the 4th power, so x must be 4 for those two to be equal. Let's do the one below it. It says log base 2 of 1/64 equals x. Rewrite it exponentially. The base is 2. Logs equal exponents. This will equal what we took the log of. Now I can rewrite 64. It's 8 times 8, which is 2 times 4, and 4 is 2 times 2. So now I have 1, 2, 3, 4, 5, 6 2's. So this is the same thing as 1 over 2 to the 6th. And then to get it out of that denominator, I can write it as 2 to the negative 6th power. Right? Take the reciprocal, but that makes it a negative exponent. Now they have the same base. 2 to the x equals 2 to the negative 6th, meaning their exponents have to be equal, and x equals negative 6. And this last one, same idea. Log base 10, base is 10, logs equal exponents. The exponent is x. That will equal 100. I just wrote the answer. And I can rewrite 100 as 10 squared. And so that means x must be 2. Go ahead and try the 3 examples on the right. The last one you may have to think about. First example on the right hand side, log base 32 of 2 equals x. I rewrite it exponentially, so I start with the base. Logs equal exponents. That log equals x, so x is the exponent, equals, the only number we haven't used, 2. Now I want to rewrite this exponentially, with the same base. So I have to factor 32. That is 8 times 4. 8 is 2 times 4, and 2 times 2 is 4. So I have 1, 2, 3, 4, 5 2's. So 32 is the same thing as 2 to the 5th power, and we were already taking that to the x power. So now, a power to a power, we have to remember those get multiplied. So it's just 5 times x. Now they have the same base, 2 to the 5th, or 5x power equals 2. But there's no exponent over here, so what do? 2 is the same thing as 2 to the 1st power, right? 2 to the 1st power is still 2. So they have the same base. I set their exponents equal. So 5x must equal 1. And then we have to solve for x. And x equals 1/5. Again, you could plug this back in and check it. Make sure it works. The next example, log base 5 of 1 over 125 equals x. Start with the base. Base is 5. This log equals x, so x is the exponent. That will equal 1 over 125. We've already factored 125 previously. That's the same thing as 5 cubed. And to get that out of the denominator, I have to take the reciprocal, which makes the exponent negative. Now that they have the same base, 5 to the x equals 5 to the negative 3, their exponents must be equal, and x equals negative 3. Now this last one. Log base 5 of 1 equals y. Start with the base. Base is 5. Logs equal exponents, and that will equal what we took the log of, which is 1. Now this one's the trickiest one, because this has a base 5, and this is just plain old 1. How do I make a 1 into a 5? Well, this comes back to, what does y have to be? What exponent could I put in here for y that could even make this equal 1? The only value that could go in here is 0. Right? So 5 to the 0 power would equal 1, because anything to the 0 power equals 1. So now I have the same base, and y has to be 0. That's the only thing I could put in there to get out a value of 1. 5 to the 0, anything to the 0 power equals 1, so that exponent has to be 0.